Hey everyone, I'm back again. I'm here to do LeetCode problem number 814, binary tree pruning. Let's read the problem. Given the root of a binary tree, return the same tree where every subtree of the given tree not containing a 1 has been removed. A subtree of a node is node plus every node that is a descendant of node. Essentially what you're doing is you want to remove every subtree that contains all zeros. So for example, if you take a look at this example right here, you have 1, 0, 0, and 1. There's a subtree right here among the three nodes, but there's also a subtree of just singular nodes on the left and the right. This left one is all zeros, so you remove it. There's only 1 0 here, so you remove it. And you're left with this tree, which is basically a linked list right here, 1, 0, 1. In this situation, you have two subtrees, this subtree of 3 nodes, this subtree of 1 node, and you remove them, and then you're left with basically another linked list. This one, you have a 0 node right here, a 0 node right here, and then you're left with this tree right here. You don't remove this 3 node tree right here because the 3 node tree subtree right here has a 1 right here. So that's what's keeping you from removing it. You have to remove the subtrees that are basically all zeros. Okay. So this is not a hard problem. I believe this is a recursion problem, but let's take a look. Tree, depth first search, binary tree. Yeah, it's definitely depth first search, but let's get started. Take a look at the constraints. The number of nodes in the tree is in the range 1 to 200. Okay, so this could be a pretty big tree. The value is either 0 or 1. Okay, so we don't have any crazy values, which is good. Topic. I thought this was a recursion problem, but based off of tree depth first search, binary tree. Okay, so I just want to record this. This is a binary tree problem. Okay, it's a tree depth first search or binary tree problem. Let me make sure I capture that correctly. Tree depth first search, binary tree. Okay, so let's design the algorithm. If the root is none, return none, right? If the root doesn't have anything, this is also if the root is none, then we don't do anything, we return none. This is also the base case for the recursion. Okay, do depth first search. And do it in, give me 1 second, I need to look something up. Okay, I just want to get the terminology correct. Do it DFS and do it in a post order manner. If you find a node whose value is equal to 0 with no left or right nodes, then prune the node. Return the root as the answer. Okay, so let's do it. If root is none, then you return none. Then this is where the depth first search happens. Left equals self dot prune tree root dot left. Right equals self dot prune tree root dot right. So you let the depth first search go, and then every time you do it, you assign it to this left and right pointer, and you keep doing that. So this is where the trick comes in. If hang on, give me 1 second. Let me think for a minute. Root dot val equals 0. Hang on, give me 1 second. Actually, this is incorrect. We're not defining new variables here to do the depth first search. We should be doing root dot left and root dot right. If root dot val equals 0 and root dot left equals root dot left equals none and root dot right equals none, then what do? You have to prune the tree, right? You do return none. The reason why you do return none is because as you go do the depth first search, and if it hits none, you found the node that you want to prune. Well, the way that you prune it is you assign it to none, either the root dot left or root dot right, depending on which one you're doing the recursion. That will now be assigned the value of none as you go back from the last stack trace, not stack, last frame of the recursion. So either root dot left or root dot right will be assigned a value of none, and that is what we want. That is how if you have this right here, if this is assigned the value of none, then that essentially prunes that node, right? And the value that we want to return is obviously return root, which is the answer. Let's test. Let me look the code one last time. If root is none, return none. Root dot left equals self dot prune tree root dot left root dot right, self prune tree root dot right. If root dot val equals 0, left equals none, and right equals none, return root. Let's try it. There we go. Okay, very good, very good. The time complexity is O of n, because that's the number of nodes that we're trying to deal with in the binary tree. And the space complexity is O of h, where h is the height of the tree. That's generally speaking what the space complexity is. The SC can be as bad as O of n. Can be as bad as O of n. Let me just document this better. Sorry. Space can, where you have a linked list, right? If you basically, the tree can be pretty bad. The worst case scenario is basically you have a linked list, and that's the space complexity is O of n, and then the space complexity can be as good as O of login where you have a balanced binary tree. Okay, but overall it's O of H, where H is the height of the tree. And so for those reasons, I'm pretty happy with this problem right here. I was able to explain it, I was able to do it, and so it was really good to practice again. Thank you all for listening. I'll see you at the next one.